Hi, welcome to another pre-recorded lecture. And today I'm going to start by explaining the 100 prisoners problem, which if you haven't thought about this, then I encourage you to try and solve it before hearing the solution. When I was about your age, maybe like the first or second year undergrad student, I saw this problem and I solved it after a while, and it was quite exciting, so I enjoyed it quite a bit. So yeah, just pause the video if you want a hint. Here's a hint. You use the material from previous lectures, from the recent lectures. If you want even further hint, then use cycle decomposition. And that's it, no more hints. Yeah, alright, so let me now explain the solution. First of all, let me remind you what the problem was. You have a room with 100 drawers and you have 100 prisoners. Each prisoner is numbered, they know their own number, and they're common, and each drawer the drawers contain numbers from 1 up to 100, just randomly permuted inside. So each prisoner comes into the room and they are allowed to open exactly 50 drawers. If they find their own number, then they win. If at least one prisoner does not find his own number, then all prisoners lose. And otherwise, they all win. So the question was, what is the optimal strategy? What is the optimal probability? And I gave an example of a strategy, which was to choose just random 50 drawers, and I explained that the actual probability of that dumb strategy was pretty slim, right? Not very satisfactory if you want to survive. So can you do better, or can you prove that there is no better way? And intuitively it seems like there is no better way, because like all the drawers are sort of the same, but so the question is, can we do better than 2 to the negative 100? And the answer is yes, we can do better, and the actual probability, the optimal strategy is about 31%. The strategy of everybody finding their own numbers is about 31%, which is, if you think about it, it's completely mind-boggling. If you compare these two numbers, like how the hell, even though 31% of survival probability is not high, but compared to 2 to the negative 100, there is orders and orders of magnitude better. 31% is much better than this number here. So yeah, and what I'm gonna prove, I'm gonna explain a strategy which gives this probability of success. I'm not gonna prove that it's optimal, but it is known to be optimal. So yeah, here is a proof. If you want to think a little bit more now that you know the answer, then feel free to pause the video again. So how do I prove it? And remember, so the rules of the game are that the prisoners are allowed to discuss the strategy before the game starts, but not after the game starts. There is no communication, no information is passed between the different prisoners. So what they should do before the game starts is that they should discuss a numbering of the drawers, just kind of left to right and bottom. So the first step is number the drawers from 1 up to 100. So let me denote by, let's say, lowercase n is going to be the number of drawers. So you just number them left to right, sort of, it doesn't really matter. 1, 2, 3, all the way up to 10, 11, 12, yeah, this is all the way up to 100. Just have a well-defined numbering of all drawers, which is the same for all prisoners. And then for each prisoner, so that's the sort of the main idea. Each prisoner numbered, let's say it's numbered I, first opens the drawer numbered I. So the first step is to open the drawer, which on the outside, so if this was 12, then you would open the drawer number 12. So you start there. And then you open this drawer and you see a number. You see some other number which is inside the drawer. Then you open the drawer numbered the drawer let me put it this way, whose outside number is the number. So yeah, anyways, so you first open the drawer numbered I, and then you see number f of I, or maybe w of I, inside of it. So in other words, the distribution of 100 numbers inside 100 drawers is a random permutation, which I'm going to denote by W. So if you open drawer numbered I, then you see W of I inside of that drawer. The next step is to open the drawer numbered W of I. So, and once you open the drawer, you see W of I inside of it, and iterate. So just keep going, keep applying this operation here. Whenever you open drawer, you see a number, and then you open the drawer with that number. So that's the optimal strategy. Now, why is this strategy good? So yeah, the trick is that it seems as if each prisoner has no information. All the drawers look the same to them, but the actual numbers in the drawers allow you to do this extra tricky step. Yeah, okay, so that's the optimal strategy. What is the probability of success? Let's see. So the prisoners win if and only if all cycles of W have length at most 50. So here it's important that W was not some specific permutation, but it was some uniformly randomly chosen permutation out of all possible permutations. So the prisoners win if all cycles have length at most 50. So what happens if what happens if they all lose? So otherwise, all cycles, otherwise W, so let me assume otherwise that W has a large cycle of length, maybe of length K, which is bigger than 50. And because the total sum of all cycle length is equal to n, right, there could be only one big cycle. So then this cycle is unique. So now what I'm gonna do is I'm gonna try to count the number of permutations which have at least one, and therefore exactly one large cycle, which has more than a half terms in it. So so how do I count? Number of bad permutations. Number of such permutations. W. The way to count it is pretty straightforward, right? So first you choose the cycle. How do you choose the cycle? When you choose the elements, the actual numbers that participate in the cycle as a set. In n, choose, so n is 100 and k is more than 50, and choose k ways to choose the numbers in the cycle. And then you have to order them cyclically, right? And that can be done in k-1 factorial ways. Ways to order them cyclically. And finally, the last step is you have to order the remaining numbers. So in other words, if you use two-line notation, then let's say you choose some numbers which belong to your cycle, and then for each of them you know where W sends those numbers. And for the remaining numbers, you are allowed to permute them in an arbitrary way. So in other words, there's n minus k factorial ways to order the remaining numbers which are not in your cycle. And they can form as many cycles as you want of arbitrary sizes. Yeah. So the total number of options is, you have to multiply all these numbers together. Total number of options for bed W is n choose k times k-1 factorial times n minus k factorial, which is n factorial over k. And this is for, so here k is fixed. It's the size of the bed cycle. But then we have to sum over all possible sizes. Total number of options for fixed k. K is fixed, and it is between 51 and 100. Now, if you sum over all k, you get n factorial times 1 over 51 plus 1 over 52 plus etc. plus 1 over 100. And then, so you can plug this into Wolfram Alpha, or write a program, and you're going to see that this is approximately n factorial times 0.69. Just the sum of all these numbers. I mean, if you sum them from 1 to, you just sum all numbers of the form 1 over n, you would get infinity. But if you sum from 1 over n to 1 over 2n, then that sum is going to be, well, anyways, this sum is equal to 0.69. That's all I can say. So in particular, the probability of success is 1 minus the probability of failure, which is you're supposed to take this number and divide by n factorial times 0.69, divide by n factorial, so you get 0.31. And again, I'm not claiming that this strategy is optimal, but it totally is optimal. And yeah, it is possible to prove that it's optimal. It's in some paper from 2006, I think. So that's the power of cycles of permutations. Now let me go back to computing some. Last time we computed permutations according to their number of cycles, and today I'm gonna try to do a more refined enumeration, and that's gonna be according to the cycle type of my permutation. And it's also useful in some situations. So what is the cycle type? Here's the definition for W, for a permutation W. Let Ci of W be the number of cycles of W of length I. So I want to record how many 1 cycles it has, that's C1, how many 2 cycles it has, that's C2, and etc. And then the cycle type, just by definition, is type of W. By definition, it's the C1 of W. I just record these numbers in a tuple, in an n-tuple of numbers. Okay. And so first of all, if I don't show you W and I just show you the sequence, maybe I should try an example. Yeah, okay, here's an example. Example, let's say W is 8, 1, 6, 4, 2, 3, 9, 7, 5, something like this. Then the type of W is what? There is 2 cycles of length 1. So it starts with a 2. Then there is 1, 2 cycle. 2, 1, 0, 3 cycles, and then 0, 4 cycles. Then there's 1, 5 cycle, 0, 6, 0, 7, 0, 8, 0, 9 cycles. So that's the type of my permutation. And the first question is, how to recover n in terms of this type of W. So if I just show you the sequence here, how do you know that n is equal to 9? And of course, this is not too hard. The answer is that because so we have 1 here, that's C1, C2, C3, C4, C5. C5 is equal to 1, that means there is a 5 cycle. And there is a 5 cycle, a 2 cycle, and yeah, so anyways, you have to sum them with weights. So n is equal to the sum of I times Ci of W. And now I'm ready to state a result which tells you the number, how many, if you fix the type, then you know n, but how many permutations of a given type are there. And that turns out to be a pretty easy problem, which I could have done in the first lecture probably, or whichever one was about the division principle. So let's say I assume that n is equal to, so I assume that I have a tuple C, which is C1, C2, etc. up to Cn. Maybe I have a vector of numbers satisfies that n is equal to the sum of I times Ci. Then the number of permutations W in Sn such that the type of W is equal to C. That number is equal to n factorial divided by 1 to the C1 times C1 factorial times 2 to the C2 times C2 factorial times etc. times n to the Cn times n factorial. sorry, times cn factorial. Cn factorial. So it's a nice product formula. And yeah, so the proof is by division principle. And so let's see, how do I, so I'd like to generate every permutation whose cycle type is C. How do I do this? Well, the idea is you just write down, so instead of, you forget about the parentheses and you just write the actual, just write all these n numbers in random order. So you choose a permutation W, W1, W2, etc. up to Wn inside Cn, and then you want to insert the parentheses. So insert the parentheses into W to obtain W prime in the Sn of cycle of type W prime equal to C, so that the cycle lengths are weakly increasing. So that cycle lengths are weakly increasing. And that can be done in a unique way. Right, so you start with W1, W2, W3, W4, W5, W6, W7, W8, etc. And then so there should be C1 cycles of length 1. So you start inserting parentheses, you make the first C1 entries to be just 1 cycles. And then you switch to cycles of length 2. So you make this into cycles of length 2, and you make so the next 2 times C2 entries are going to form cycles of length 2, and etc. Yeah, the next one is going to be 3 times C3. Each cycle is going to have 3 elements, and etc. And because of this equality here, you're going to finish using all of these n elements of W. So, and let me denote this permutation by W prime. So this new permutation is W prime. In cycle notation, it is just written in this form. So the question is, well, first of all, clearly the type of the permutation I have obtained is equal to C. So that's nice. And then also the cycle length are increasing, right? So that's the yeah, I guess there is a problem here. Weakly increasing. But the question is, first of all, do I get any possible W prime in this way? And if yes, in how many ways? And well, first of all, it's clear that I get every one, right? Because given a permutation W prime, I can order the cycles so that the lengths are weakly increasing, and then I can just ignore the parentheses, and I'm going to get the permutation. So clearly the map is surjective, and now the whole game is about the size of the preimage. So in how many, if you give me W prime of type C, in how many ways can I write it down as such product of cycles? And the answer is very easy to compute. Right? I can take cycles of length 1 and I can permute them between each other in C1 factorial ways. They have to come before all the other cycles because the lengths are weakly increasing, but between themselves they can be permuted in an arbitrary way. So so I need to divide by the following product. So for each I I can permute the cycles, the cycles of length I in Ci factorial ways. And then also inside of each cycle I can permute the elements cyclically. Right? So I can 1, 2, 3, I can also write 2, 3, 1 or 3, 1, 2. So I can choose the first element in I ways. Each cycle choose, so each cycle has length I, choose the first element in I ways. In particular, the number of I cycles is Ci, so the total number of options is, so I choose the first element in each of the Ci cycles, and I also permute the cycles. And then I take the product over all I n, I from 1 up to n, and then, and then just by the division principle I have to divide n factorial by the size of each preimage. So we are done by the division principle. So okay, now let me try. And this formula, the proof was very elementary, right? Just division principle, nothing else. And well, now I'm going to try to apply. Already this formula has a couple of nice applications which are non-trivial otherwise. So, and the first one is going to be pretty trivial. The first example is, let's say that the type of W, let's say it is equal to 0, 0, 0, 0, 1. So let's say the last Cn is equal to 1, C1, C2. All the other ones are equal to 0. That means that W is a single cycle. So, but if I just literally use this formula, number of such W's is equal to n factorial over each of these Ci's is going to contribute just 1 because they are all 0. But the last one, n to the Cn, so the last one is going to be n to the first times 1 factorial. And the answer is n minus 1 factorial as expected because that's the number of n of permutations which are single cycles. Now the next example is actually much more interesting. So here's the next example, which is, if you know about graph theory, which I think is one of the prerequisites, then this has a nice interpretation. So the question is, what is the number of perfect matchings of the complete graph K to n? Which, if you know what it is, then great. If you don't remember, probably, then let me show you. Maybe n is equal to 3. What you do is you write 6 numbers on a circle. So here's a circle: 1, 2, 3, 4, 5, 6. And then you want to, maybe should I do another? Yeah, let's try n. Well, okay. Here's n equals to 3. So you want to match. You want to just split them into pairs. You want to split them into pairs in an arbitrary way. So maybe, and this is a perfect matching of the corresponding complete graph. But yeah, maybe let's try n equals to 2. N equals to 2 is I can actually list all of them pretty quickly. No. 1, 2, 3, 4. So in how many ways can I match these 4 numbers? Can I split them into pairs? Well, the answer is in 3 ways. You can either do 1, 4 and 2, 3, or 1, 2 and 3, 4, or 1, 3 and 2, 4. So for n equals to 2, the answer is 3 ways. But what is, so here the answer is 3 ways, 3 perfect matchings. And yeah, and in general, so how do I state this in terms of permutations? Solution. This is the number of permutations in S2n of type what? So I want to partition numbers into pairs, and that means that I want to treat each pair as a 2-cycle. So I'm only looking at permutations for which all cycles are of length exactly 2. Of type 0, so C1 is equal to 0 because there is no 1 cycles, and then C2 is equal to n. 0, 0, 0. C2 is equal to n because the total number of letters is 2n. Yeah. So again, I'm allowed to use this formula here to by the way, such permutations are called also known as fixed point free involutions. So an involution W, by definition, W is an involution. A permutation W is an involution if and only if W squared is the identity permutation. So if you apply it twice, you get the identity, and that means that all cycles of W are of length either 1 or 2. And fixed point free means that there should be no fixed points. So there should be no cycles of length 1, and therefore they all have to have length 2. Anyway, yeah, I'm going to discuss involutions a bit later, but for now let me go back to applying this formula here to compute the answer. So the answer by the above formula is 2n factorial over the only not equal to 1 term is 2 to the c2 2 to the n times c2 factorial times n factorial. Yeah. So that's the number, and this number actually has a name, right? It's usually denoted by 2n minus 1 double factorial. So here, by definition, what is 2n minus 1 double factorial? That just means that where 2n minus 1 double factorial is by definition 1 times 3 times is just the product of all odd numbers between 1 and 2n minus 1. And why is that product equal to what's written down here? Let's see. So you have 1 times 2 times 3 times 4 times 5 times 6 times etc. times 2n minus 1 times 2n in the numerator, and so that's and in the denominator we have 2 to the n times, and yeah, let me write it down like this. 2 to the n times n factorial is 1 times 2 times 2 times 2 times 3 times 2 times 4 times 2, etc., all the way up to n times 2. So these are just basically out of all these numbers, in the denominator you have all even numbers. And so you cancel them out. 2n cancels with 2n. 1 times 2 cancels with 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8, and etc. And you are left with only odd numbers in the numerator. So that's where the double factorial comes from. And yeah, in particular, these three ways is secretly it's 3 double factorial, which is 1 times 3. So the next number is going to be, for n equals to 3, the answer is going to be 1 times 3 times 5, which is 15, I think. Okay, so, and that's a nice application, right? Completely combinatorial problem. A priori has nothing to do with permutations, but the easiest way to use is to use a formula for permutations. Okay, now let me mention one nice trick that we used in the proof, which was, there was sort of this weird operation where you take the one-line notation, then you insert the brackets, or you maybe remove the parentheses out of that permutation, and then you get, so you kind of switch using in this way between cycle notation and one-line notation. And of course here the problem was that the cycle notation can be written in many different ways, so there's some freedom. And so let me try to fix that problem, and let me try to introduce the canonical. I tried it already, but let me try to be more explicit. Canonical cycle notation. So if you want to write a permutation canonically, then the conditions are that in each cycle, maximal element comes first. So that removes the freedom of permuting cyclically the elements inside of each cycle. And the second condition is that cycles should be ordered so that their maximal elements increase left to right. So clearly these two conditions force your cycle notation to be uniquely determined. And let me give you an example. So I have an example here, which is that W 3 1 5 2 3 8 9 4 7 6. So that is in canonical form. Why? Because the maximal elements are 3, 5, 8, and 9. Each maximal element is first in each cycle, and they increase from left to right. So this is in canonical form, but if I try the same but I permute, maybe 1 3 5 2 3 8 9 4 7 6, this is not in canonical form. Or if I permute 5 2 3 and 3 1 8 9 4 7 6, these are not in canonical form. Okay, and you may say that it is stupid, that I'm just choosing some convention which is unimportant, and you're going to be right. But let me tell you a nice result, which is pretty weird, and it's pretty useful. So lemma, and it's called the Foata transition lemma, also called the fundamental bijection by Stanley, and there's some other names as well. So the idea is that you take the canonical form like this, and then you just remove the parentheses. Let W in SN be written in canonical form, canonical cycle notation. And then let f of W be another permutation, be obtained by removing all parentheses. And then f is a bijection from SN to itself, which is crazy. But yeah, let me show you an example. Here's an example for n equals to 3. So I already gave you a list of permutations and their cycle notations. So here are all possible canonical forms 1, 3, 2 of cycles of canonical forms of cycle notation, canonical cycle notations of all permutations in SN. Each permutation appears exactly once. Now I do the same, but I remove the parentheses. 1, 2, 3, 2, 3, 1, 3, 1, 2, 2, 1, 3, 1, 3, 2, 3, 2, 1. And you see that what I got on the right are all permutations exactly once without any repetition. So this has to do with I chose these conventions, although they seem arbitrary, they are chosen very carefully. And yeah, and in particular, if I wrote like instead of 2, 3, 1, I wrote 3, 1, 2, which is the same permutation as this one, but it would have appeared already for this cycle here. Right? I have also some freedom to write this cycle in a different way, but then if I maybe write it as I can maybe write this cycle as 1, 2, 3 also, but then it would have appeared here. So it is a delicate game to choose all these conventions correctly. Yeah. So all right, let me try to prove this lemma. And the proof is that the goal is to construct the inverse map. So I want to invert my bijection. In one direction it's easy, you just ignore the parentheses, but the hard part is to reconstruct the parentheses. So given let's say given a permutation V in Sn, the goal we want to find W in Sn such that f of W is equal to V, and show that it is unique. Okay, so maybe let's say I try some example. Maybe I just write down a random permutation. Maybe, for example, maybe V is in one line notation is 5, 2, 9, 3, 6. Yeah, that's probably not that interesting. Okay, 5, 2, 4, 3, 6, 1, 9, 7, 8. Something like this. So that's V, and then question is, what is W? How do you find the cycle? So where do you insert the parentheses so that after you insert the parentheses, the result would be in canonical form? Like for instance here, you see that the result is not in canonical form because 3, 6 is 6 is the maximal element, so it has to come first in the cycle. So this way of inserting the parentheses does not quite work. And similarly for this cycle here, there's also 1 is the first guy, even though 9 has to be the first. So yeah, and the idea is pretty simple. So how do you find a place to insert these parentheses? Well, you observe that okay, let me try to give a definition. Let's say so here's a definition. If you write v as in one line notation in v1, v2, all the way up to vn, then we say that vj is a left to right maximum if vi is less than vj for all I between 1 and j. So in other words, so it's a left to right maximum if it's bigger than all the elements before it. And such elements are also called records. And the reason is that if you think of v1, v2 as your, like each day you bench press and you record the weight, then at some point you lift more than you did like on all previous days, and that's where at that point you hold the record. So historically, the first one is always a record because you just started, but then after a while it gets harder and harder. Anyways, but all these numbers were records at the time where they were achieved. Yeah. Anyways, the point is that you can. The crucial observation is that the description here makes sure that the first element of each cycle is a left to right maximum. So what you do is you just insert an opening parenthesis before each left to right maximum. For example, here I just take the same permutation and let's see what are the left to right maximum. Let me get this out of the way. 5 is the left to right maximum. Then the next one is 6, and the next one is 9. So you insert an opening parenthesis before each left to right maximum. And then you also insert closing parenthesis where appropriate, because there is a unique place to insert the closing because you want the opening ones to match the closing ones, and you want all numbers to be between some pair of parentheses. And that's it. What you get is a canonical cycle notation. So let me, I guess I'm almost out of time. So exercise, this W is in canonical form, and it is unique. So no other choice would produce no other choice of parentheses would produce a permutation in canonical cycle form. Yeah. So next time I'm gonna start by discussing the several nice applications of this very weird bijection. Thank you very much. Have a nice weekend, and I will see you all on Wednesday.